Okay, so I'm Michael Bender, and this is joint work with Martin Farage-Colton and Bill Kuzmal. And the point of this talk is to explore the question, what does dynamic optimality mean in external memory? So that's what this whole talk is about. Okay, so I'm going to begin with just a brief history, just a brief introduction to standard dynamic optimality. And if we're going to talk about standard dynamic optimality, the first thing I need to do is say what a search tree is. So this is a little bit of the history of balanced binary search trees. I think the first balanced binary search tree was the AVL tree in 1962. Later on came red-black trees, weight-balanced trees, and much later data structures like treeps. And these are all very different data structures, but they're all kind of in the same class of data structure as well, because all of these data structures maintain the balance of the tree by performing rotation. So these are all rotation-based binary search trees. And what a rotation means is if you've got some nodes, you take one node in the tree, you want to maintain the log depth. And so in order to maintain the invariant that the depth of the tree is order log, maybe you rotate, so you move one tree up towards the root, which also moves some neighboring trees down towards the leaves. Right, so these are rotation-based balanced search trees, and this is what allows you to get log depth, and therefore all operations cost log. Okay. But very early on, people observed that for some workloads, we can do much better than log per operation. And here's a simple example showing where you can have a data structure that adapts to some workload so that it can do better. So say we have a round-robin workload. So we're accessing key 1, 2, 3, all the way up to n, and then repeating over and over again. And in this case, it's possible to make a tree structure so that the access time is not log n, but is actually constant. And so we could start with a tree that's just a very unbalanced tree, just a list of all the elements in order. We access 1, and then after we've accessed the element 1, we sort of rotate it down and rotate 2 up. So then we access element 2, element 3, and so forth until we have this whole tree. We've accessed all the elements. And then even for linear cost, we can afford to rebuild the tree again and repeat the process. So here's a simple example where we have a data structure that adapts to a particular distribution and performs its operations in constant time rather than log time. OK. So in the mid-'80s, this got Slater and Tarjan to think about the following kind of amazing question, which is, could there actually be a single best tree? Sort of one tree that is best for all possible distributions, and it just adapts to all possible inputs. So, and they formalize this by defining the notion of dynamic optimality. So a binary search tree is dynamically optimal against a class of rotation-based binary search trees if the tree is constant competitive with every other dynamic search tree from this class on every input. So to say this differently, a tree is dynamically optimal if the way this tree performs on every possible input is constant competitive with every possible rotation-based search tree in this class. And this also includes rotation-based search trees like the one that I showed on the previous slide that are actually tailored to a particular input.
What does constant competitive?
So constant competitive means that, yeah, thanks for asking questions. The more the better. So notice I actually smiled for the first time when you answered the question. So constant competitive means that, that our tree takes some amount of time. And if you look at the best possible performance of the tree in this class, it's, it's at most a constant factor better. So maybe our tree has got some cost on a workload, and no other tree can be more than twice as good. So that means we're constant competitive because we're within a factor of 2 of the best possible. Right, so that's what we mean by constant competitive. And this is what we mean by dynamic optimality. And it's kind of an amazing notion. And there's a subtlety here, which is, again, you're dynamically optimal with respect to some class of data structures. And in this case, the class of data structures is rotation-based binary search trees.
So I understand correctly that the rotation can depend on the input. So if first the input is fixed, then first the input is fixed, then the queries come along, and I can choose the rotation knowing
The queries.
the whole sequence of queries.
Well, when we talk about dynamic optimal and constant competitive, it's usually you see the sequence of queries only that you've seen so far, but you don't get to see the future. So normally the way you think about it is our tree T doesn't get to see the future. It has to make its decisions just based.
But does the adversary tree that I'm trying to match?
Yes, but the adversary tree gets to see the future. So because the adversary tree, it's this rotation, it's from this class, and that can even include some tree that's designed to perform well only on one workload and terrible on every other. But our tree needs to match it. That's right. So really good question. And again, like the more the better. I suddenly feel I'm interacting with people, which is a new experience after COVID. OK, so it's an amazing concept, even to consider that there could be such a tree, and we don't actually know whether there is one. So it's been conjectured that the splay tree is dynamically optimal, and I think many people believe that it is, but we don't know how to prove it. And this is one of the most important open questions in data structures. There is a data structure called the Tango tree that's within, it's not constant competitive, so it's not a constant factor of optimal, but it's within a log-log factor of being dynamically optimal. So we don't know how to be constant competitive. We do know how to be log competitive.
So is the Tango tree not constant competitive, or simply it hasn't been proven?
I suspect that it is not, and I don't know that for certain. So I suspect that it's probably been proven not to be, but I'm saying that with great authority, and I actually don't know. OK, so there's been lots of work on dynamic optimality, and I'm not going to go into it here. So now I'd like to go to the second part of the talk, which is, well, that's what the title said, which is how can we think about dynamic optimality in external memory?
Just before that, just to make sure I understand definitions, is it that any balanced tree now is order log and dynamically optimal, or order log and competitive, or no?
I think any balanced search tree is log competitive,
Yes.
just because we can, like the best that you can do in internal memory is a constant time per operation. And the worst you can do is log time per operation in internal memory. So yeah, great question. So now let's talk about external memory. So the first thing I want to do is explain what we mean by external memory. OK, and this is the external memory model. It's a 2-level memory hierarchy. So we have a small internal memory of some size m. In this talk, we're going to view m as being very, very small. We've got a small, particularly small. So we've got a small internal memory, and then a giant external memory. This could be, we're going to model it as being of unbounded size. And when you operate on your data structure, most of the data structure is stored here in external memory. And so if you want to access some data, you first need to bring the data into the internal memory, and then you can access it. And you transfer data between these two levels of the memory hierarchy in blocks of size, some blocks of size b. So we're always going to transfer contiguous chunks of data, and we're going to say that the size of data is b. And we can think of this as sort of any two levels of the memory hierarchy. So this could be cache and RAM. This could be RAM and SSD. This could be, there are lots of different levels, and memory hierarchies are actually getting more complicated. But if you've got two levels, we can think about it in this way. Now, the cost is measured in terms of the number of block transfers. So we don't care what the CPU cost is. We care about how many of these block transfers that we do. Because block transfers in many workloads, the number of block transfers is actually the dominating cost. I think at some point many years ago, Martin and I gave some tutorials where we were, when there were rotating disks, and we were talking about the difference in access time between accessing a piece of RAM or accessing a rotating disk. And we had some wonderful metaphors. And I think one of them was that if the cost to access a disk, like if we can view that as like the walking speed or maybe sprinting speed of a Galapagos tortoise, then the cost to access RAM is the speed to access RAM is the escape velocity from Earth. So like there's really different access times between different levels. And so in the external memory model, we're just going to count the number of block transfers. That's the cost. All right?
It's no longer the case.
It's no longer, it's not the escape velocity from Earth, but it's still orders of magnitude. Or maybe you have to get faster than a Galapagos tortoise. OK, so dictionaries are extremely interesting in external memory. And the classic dictionary is for external memory is called the B tree. And this is I'll just give an explanation of the B tree. This is an old cartoon of a B tree, which at the last moment I put in my talk. And because actually I was explaining this to John's dad, and I was showing him this picture. And I was saying, hey, look, this is a cartoon of a bee tree. And John's dad says, I don't get it. And so, of course, I explained, there's the tree, and those are the bees. And John's dad says, those aren't bees, those are wasps. Yeah, bees don't make nests like that. Those are paper wasps or something. They're not bees. But I'm going to talk about this part of the picture. So when you have a bee tree, you have a tree. Instead of having fan out of 2, you have a fan out that is ordered the block size. And the reason you do this is because we want the B tree nodes to have size that's the block size. So each one of these nodes that looks like a point, this really should be a block. And it costs 1 to access every block. So this means that when we search in a B tree, there are log B levels. And so the cost of a search in a B tree is log base B of n. And in order to maintain the invariant that the height is log base B of n, we have siblings that, if siblings get too empty, you merge them together. If a node gets too full, you can split it. And so we can maintain this invariant that the fan out is in the range block size over 2 to the block size. So the height is log base b of n. And the result is that all operations take cost log base b of n. Like searching, inserting costs 1 per level. OK, so this is a B tree. And so we want.
So you have a rotation here, or there are no rotations?
So you're prescient. Now you're asking the right question. Right, so you're asking exactly what the next slide is. Which I appreciate.
That was my intention, because I don't think I understood the previous one. How do you get log n base b if there is no rotation?
Good, all right, so let me say this more. So if you have 2 nodes, so all of the leaves are going to be at the same depth. So if all the leaves are going to be at depth log base b of n. And so when you insert into a B tree, you insert, you search, find a place to insert into a leaf. And if there's space in the leaf, you insert there. If it turns out that a leaf is already full, there's no more space to insert, then you split that leaf into 2 leaves. Now the leaves are half full, so there's space. And when you split these 2 leaves, now you've increased the fan out of the parent by 1. And so that means that sort of as you split more and more leaves here, you create more parents and more grandparents and so forth. And eventually, maybe you need to increase the height of the tree by 1 or decrease. And if you're deleting and a node becomes too empty, then you merge with a sibling, which then decreases the fan out of the parent by 1. And so the operation, as you said correctly, it's not rotations, it's splits and merges. Like a 2-3 tree. Or
sorry. So does the range have to be like the vector block?
Say that again?
Does the range matter? I mean, could it be like b over 3 or?
Yeah. So the question is, does this range matter? And the answer is no. In fact, there's a whole bunch of interesting work in some cases about trying to get the range sort of as tight as possible with random inserts and trying to analyze this. But no, it doesn't matter because it just affects how you do your. Yeah, whether you merge or split like multiple nodes or just 2 at a time, that doesn't matter.
So, sorry, I have a picky question.
Yeah, good.
So when the root reaches b plus 1, what do we do?
Good question. So one of the things that I was contemplating whether to say is this invariant holds true with every node except for the root. So the root we're going to allow to have, a fan out as small as 2. And as large as b. And so when it gets to b plus 1, you split, you make a new root that has fan out 2. Very nice. So the first thing to observe about B trees, as Sepher already did, is that B trees are not rotation-based. So already B trees don't fit into the notion of dynamic optimality that we think about in internal memory because they don't do rotations. They do splits and merges. So this question, how do we move, keys move up and down in the tree? I think that's a little telegraphic. What I was trying to say is the whole point of doing rotations is to move the elements that you're trying to access in the future close to the root of the tree so that you don't have to go down the whole tree to access them. Right? So you want things that you're going to access frequently to be near the root of the tree. And the question is, with splits and merges, can you still do that? Yeah?
And a big difference between binary trees and d-ary trees is that an asymptotically smaller fraction of things can be near the root.
Oh, very nice. That's right. Right. So it's an asymptotically smaller fraction of things that are near the root. So if in a real industrial strength B tree, like 90, 95, % of the elements are actually just in the leaves. But the question is, can you even move any elements to the root, closer to the root at all, so that we can even think about dynamic optimality? And the answer is yes, we can. And we can do this also via splits and merges. For example, suppose that, so x is some element, it's a pivot element, or we can make this a pivot element, split so that x is one of the pivots, and now x is closer to the root, and so we don't have to go all the way down the tree to access x. So there is still, hope. We can, in fact, have different access times so that we can talk about dynamic optimality in B trees. But we also said dynamic optimality is in terms of a class. You think of dynamic optimality with respect to a class of data structures, and we can say that this class of data structures that includes the B tree is a merge-split tree. It's where we merge and split neighboring nodes in order to maintain the balance. Yeah?
So if there were a bunch of different types of rotation-based trees, are there also different types of merge-split trees?
There are a lot of different merge-split trees, but somehow, I'm not sure there are as many as one would think, because people view this as sort of, a little bit grungy. But there's different ways of choosing when you merge, when you split. So for example, there's something called weight balance, which is one way of determining when you merge and split. And then there are other ways. So the different triggers of determining when to merge and split. But, oops. And actually there is good news with merge and split trees, which is there is in fact a data structure that's dynamically optimal against merge split trees as well. And this is a result, Bose et al. From 2008. So there is in fact a notion of dynamic optimality with respect to merge split trees. And this is good news, but it's also kind of vaguely disappointing news. And that's because the data structure actually doesn't do, this data structure that's dynamically optimal actually doesn't do that well. For example, say you have the same round-robin workload that we talked about the beginning of the talk, axis 1 to n, 1 to n, 1 to n. Well, this workload actually just takes log base b of n time per operation. It's sort of no better than a non-dynamically optimal tree. And that's because no data structure in this class can do well for these round-robin workloads. The point is, this is actually not that powerful a class of data structures. And if you're thinking about being instance optimal, well, this data structure is not very good at adapting to workloads. OK. So the conclusion is maybe merge split trees are just not the right data structure for us to consider when we're talking about dynamic optimality in external memory. OK. So let's go back to rotations for a bit. Just a few years ago, in 2019, Domain et al. Showed how to define some notion of a rotation. It's not exactly a rotation. It's more like a rotation operation for B trees. And they proposed a data structure that they called the Belga B tree that's within a log-log factor of dynamically optimal, also in external memory. So instead of doing mergers and splits, they do some sort of rotation. Now, in external memory, they're within a log-log factor of dynamically optimal among all of these class of rotation-based external memory data structures. And this is sort of nice because now external memory and internal memory are kind of in the same situation as each other. Okay, we don't know how to be dynamically optimal, but we know how to get within a log-log factor of each other. And this is kind of the end of the background, because what I'd like to do in the third and last part of the talk is explain why B trees and rotation-based B trees are just not the whole story. OK. And the reason why is because B trees are often in external memory, they're just not the right data structure. And they're not the right data structure, let's see, because they're suboptimal for insertions, deletions, and updates. So B trees are optimal for queries. So there's a simple information theoretic argument that you can use to show that B trees answer queries optimally, or comparison-based queries optimally. But in external memory, there's this really interesting asymmetry between queries and inserts and deletions and updates, where you can actually perform insertions and so forth orders of magnitude asymptotically faster and orders of magnitude faster than you could perform searches. And this is something that I'm trying to decide what to say. This is an important part. The fact that this is true is an important part of my life and also an important part of Martin's life. And we started a company based on this observation. We have a file system based on this observation. So Martin, feel free to interject at any point in time because this is warm and fuzzy for both of us. OK, so I'm just going to, let's see, we're going to focus on updates for simplicity. And I just want to quickly do an aside to explain what I mean by this notation, then I'll go back. So dictionaries store key value pairs. So when you have a dictionary in theory or also in practice, you store key value pairs. So when you search for a key, what this means is you give a key and you want to find the value associated with this key. When you insert a key value pair, well, you're just inserting the key value pair into the data structure. When you delete a key, then what you're deleting is the key value, whatever key value pair is associated with this key. But the relevant part, and the reason why I put this slide here, is actually to explain what I mean by updates. And this will be important for later in the talk. Is when you update, what you're doing is changing the key's value to v. So you've got a key that's already in the dictionary, and all you're doing is changing its value. So the point is that the update doesn't actually change the set of keys in the dictionary, but it changes the values associated with the keys. And that's going to be important at the bitter end. And so then this is just the slide again that I want to explain why there's this insert-search asymmetry. And this is based on a technique that appears in a bunch of places, notably Brodel and Fagerberg, where you do something that's B-tree-like, but now you add buffers to the data structure. And so we have the same tree structure as before. We still have nodes with size b. So the nodes still have the size that's the block size. But now we're going to reduce the fan out. So instead of having a fan out that's equal to the block size, we're going to have a fan out f that's potentially much, much less than the block size. But we've still got these big blocks. And so what we're going to use, we've still got these big nodes, and we're going to use the node to maintain buffers that are going to trap insertion and deletion and update operations. So if we have a node that has size b, and we have a fan out f, then associated with each edge down the tree, we're going to get a buffer of size b divided by f. Right?
So it's some sort of lazy.
Exactly that.
lazy thing that's happening.
It's like it's something lazy that's happening. Instead of inserting all the way down, to a leaf, we're going to put an insert and somehow trap it in this buffer. And when the buffer fills up, we flush.
My favorite analogy is a B tree is if you order something on Amazon, they'll put the pen you ordered in a truck by itself and drive it all the way to your house. And here you have like the regional warehouses.
So I like the lazy bee tree. It's the bee that's
As opposed, I said,
Bees are famously lazy.
I don't know if it was that on purpose, because I'm used to thinking about busy bees, but you're right, lazy bees are more to the point. And so now I just have a bunch of slides that are saying exactly what you said. The buffer collects insertions or deletions or updates and collects them. Once the buffer fills up, then you flush. So you flush this buffer all the way down to this child node, and then these elements end up in these buffers here. And if you're searching, so how do you search? Because now an element that you're looking for, it could already have reached the leaves, or it could be at any of the buffers on the way up towards the root. But in the external memory model, we're not interested in CPU operations. We're just interested in I/O operations and block transfers. And it costs 1 to read in an entire one of these nodes from disk, read through it, and write it out. So that just costs 1. So to search for an element, you need to search in all the buffers on the way to a target leaf. But that just costs 1 per level. And so what this means is that the queries take time take time the height of the tree. So the height of the tree is log base the fan out of n. And so queries, you just search in all the buffers on the way down to the leaves. But updates and insertions and deletions are faster because every time we flush an element from one level of the tree down to the previous level, it doesn't get flushed alone. We're not sending, as Martin said, we're not sending a pen, directly from your favorite fountain pen store all the way to you. You're, filling a truck full of fountain pens and sending them all to you. And so every time you flush a node down one level of the tree, it gets flushed with b divided by f other elements. And so what this means is the amortized cost to insert or delete or update is the height of the tree divided by the block size divided by the fan out. Make sense? And this turns out to be 1 to 2 orders of magnitude in practice, which is why we could make a file system and a company and key value store and all this stuff out of this observation, because it's the asymptotics make a difference. Okay.
Could I
Yes,
just
please.
ask, So for the queries, am I right that if you go down, if you check the stuff, the first time you see a key value, that's the latest one?
Very nice. That's right. The first time you see a key value, that's the latest one. And so that's the thing that you're looking for. And so what you're actually inserting is messages, because I could insert an element, I could delete the element, I could insert it again, I could change, I could update its value, and I could do this over and over. And so you could have the same key value, the same key on every single level of the tree, but it's the highest buffer that contains the information that you actually want.
Or not.
Or not.
Suppose your message is increment the value.
That's fine.
And this it seems like a small distinction, but in fact it's a huge part of designing algorithms for these sorts of things, is coming up with clever messages that do things and then they compose. And so you might actually have to look at the entire path because it's a rich class of messages.
Yeah. And when we built things, we really did use a very, very rich class of messages. Yeah.
So if I never search the way you describe it, is that I may size of my tree is proportional to the number of updates, not n.
That's right. And that's also, so just to echo what you said, well, you could have this issue where where you could have a tree that's based on the size of the updates, not based on n, because you could be re-updating, but somehow you're doing these updates, but they're never quite flushing down to the leaves. And so things are filling up. And so it is true that when we build some of these things, we actually did put in some kind of artificial or preemptively flushing things so that you didn't get too much cruft staying in the buffers.
Although updates are not a problem because the top of the tree is asymptotically smaller than the leaves. It's deletions that's the problem, because you could include deletions.
That's right. Yeah, I should have said that.
Be deleting a huge fraction of the leaves.
That's right. OK. So let me just plug in some example values. And I know it. All right, so let me plug in some example values. One relevant value is, what if the fan out is square root of the block size? And the nice thing about this is if the fan out is square root of the block size, well, log base square root of b is the same as log base b. So that means the search cost is the same as the search cost in a B tree. On the other hand, you know, f log f of n divided by b is log base b of n divided by square root of b. So with this choice of fan out, we now have a data structure that queries as fast as B trees, but inserts asymptotically faster. And so from an asymptotic point of view, there's actually no reason ever to use a B tree, because this is a data structure that strictly dominates it asymptotically. But we can choose a different value for the fan out. For example, say the fan out is just 2. Well, if the fan out is 2, now the height of the tree is not log base b of n, but it's log base 2 of n. But the insertions and updates and deletions are extremely fast because it's log base 2 of n divided by the block size, right? So 2 log base 2 of n. So the fan out is 2. Insertions are much, much faster. OK, so now there's actually this trade-off because the smaller you make the fan out, the slower you make insertions. Just a little bit slower, but queries, thank you. The slower you make queries, and even asymptotically slower, but you really improve insertions by a lot. So now let's start to talk again about dynamic optimality. And this means that there are actually 2 parameter regimes where we can care about dynamic optimality. One of them is where you have a query-heavy workload. There are just not that many updates or insertions or deletions. And then B trees are just fine. And we can use Belga B trees or come up with something better. But the area that Martin, Bill, and I are interested in is this update-heavy workloads, where you have where you have insertions and deletions and updates, and you have searches, but it's more about but it's heavy on updates. And that's the case where we want to use this sort of buffered propagated trees because they're asymptotically faster than B trees. So in this talk, we're interested in what should dynamic optimality mean in the update-heavy setting. And we'll give some, in the last few slides, we'll give some intuition. But this is really mostly open questions and well, it's not mostly open questions. There's lots of closed questions, but there are more open questions than closed ones. OK, so let's figure out what the knobs are that we can turn. We want to make an adaptive buffer propagated tree. And there's lots of flexibility that we have to adapt dynamically to a workload. And I'll describe the pieces of flexibility. One of them is that different nodes can have different fan outs. And I explained before why you might want some nodes to have a large fan out and some to have a small, depending on whether it's mostly insertions or deletions that are passing through that node. And another important piece is the pivot selection. And I'll describe, probably just repeat with a little more details this in the next slide, why pivot selection turns out to be important. We want to select pivots somehow to split parts of the workload that are more insertion heavy from parts that are more query heavy. And of course, the structure changes over time. So we want the structure to be dynamic. OK, so these sort of the idea of kind of the knobs that we have for these adaptive buffer propagated trees. And so now I can actually describe the question that we're interested in, which is, does there exist a data structure that's dynamically optimal against the class of all buffer propagated trees? And we don't know the answer to this. I have no idea, but I'm very excited by it. But I'll say what we do know. And the point is that we want the point of the dynamic optimality is to balance these competing demands of updates, which require small fan out to be fastest, and queries, which require large fan out to be fastest. And so this is the question that yes?
I
think now is a good time to say that in standard dynamic optimality, the reason you never think about updates is because the cost of updates and the cost of queries is the same. There's no asymmetry, there's no competing demands. And so I think the point of this slide is that in external memory, because of this asymmetry, you in fact, it doesn't make any sense to study, or makes less sense to study dynamic optimality if you're not going to study updates. So it really separates it from the normal RAM setting.
Thank you. Yes. That's just what I was going to say in the next sentence.
No way. Well, then I'll shut my mouth.
No, it's not. I appreciate it. It's not. I just thought I would act wise. No, don't shut your mouth. It's nicer this way. Okay, so I just wanted to put in a different picture that's saying the same thing. So this is a picture showing a key space from -infinity to infinity. And you could have part of the key space where most of what you're doing is updating, and another part where most of what you're doing is querying, and another part where it's mostly what's doing updating and so forth. And in your data structure, you have different nodes in the tree that are representing different parts of the key space. So in a part here, you'd like to have your nodes have small fan out. In a part here, you'd like them to have larger fan out. And so I just wanted to say the same thing with this picture. So we need to choose the node fanouts and pivot keys based on workload, sort of which parts of the key space are update heavy and which parts are search heavy. And then when you have pivot selection, you'd kind of like your pivot to be close to this barrier here so that it can separate update, so that it can separate this key space that's update heavy from the part that's query heavy. Yeah?
So I think I just realized I missed something.
Uh-huh.
So in this external memory model, there were these two parameters, N and B.
Right.
And I understood the B is, whenever you go down to a node, you can retrieve this thing in a block. Where does what role does M play in the whole discussion?
So that is a great question. And I'll answer this sort of theoretically and also a little bit in practice. So theoretically, we're going to say that N is so much bigger than M that M doesn't matter. So theoretically, we're going to say that you've got this tree here, it's a big tree here, and M is sort of caching the top part of the tree. So because you have a memory, you have a memory, you're running this B tree, and what the memory is actually doing is caching the top part of the tree, so that actually all operations in the top part of the tree come for free, and we're only concerned in the bottom part of the tree. Now, if M is polynomially smaller than N, then we can just ignore that, because that just changes operations by a constant factor. Now, in reality, it turns out that M is often, it's smaller than N, but it's not polynomially smaller than N. And so if you're actually building a B tree in practice, this M term matters a lot. In this talk, I said M once because I was legally obligated to, and it's just in the fine print.
What's the parameter M?
Oh, M is the size of internal memory. Right, that's why I only said it once. OK. So this is the key space. Choose the fan-outs, choose the pivots, and change the data structure over time. And do this adaptively based on the workload. All right. There's just a few slides left that I'd like to do, which is saying what we know so far, and then I'll say what we want to do. So first of all, one of our results is a data structure that we call a Jello tree. And I don't remember exactly why we called it a Jello tree, except for I have this image of sort of Jello kind of jiggling around and maintaining its structure.
Also, it's based on a b to the epsilon tree, so it was required to have an epsilon.
That's right. Right. That's an epsilon. That's not bad handwriting on my part. So this is our first result, which is that the Jello tree is statically optimal. So what statically optimal means is that for workloads consisting of queries and updates, the Jello tree is dynamically optimal against the class of static buffer propagated trees. So if you look at all, and so now I need to make sure it's clear what I mean by a static buffer propagated tree, which is because we're only doing updates, the key space is not changing. The set of keys in the data structure is always the same. And therefore, we can say that a static buffer propagated tree, we never change the pivots, we never merge or split. The only thing that's happening is these buffers are filling and emptying as the updates and queries get flushed down the tree.
And this theorem follows crucially from a multi-wave bandit, multi-arm bandit analysis of how to pick the pivots.
Right, because picking the pivots is important. So the Jello tree is statically so the Jello tree is a dynamic data structure, and it adapts to the workload, but it is statically optimal, by which we mean it's dynamically optimal when the class of data structures that we're comparing against are static. Okay, so that's our first result.
I didn't understand. What does it mean to be static? A static buffer propagated tree? What's the difference?
Should I say it? Do you want to say it this time? Go for it.
You pick a static buffer propagation tree doesn't get to change its buffer, its fan out of anybody, it doesn't get to change the pivots.
Right. Right.
At the beginning of time, you hand it, because we're only doing updates. This is the technical reason we're only doing updates, because then you're not changing who's in the set. If you can't use a set, you build your tree, and now you have a workload, and that's this class. And static optimality is the thing that has been studied, and we are statically optimal.
And I think it's kind of nice that you have a data structure. It doesn't know what's optimal. It doesn't know what's the best thing to do. It can't see the future, but it naturally adjusts so that it's as good or better than any other tree that is static.
So the static tree that you're fighting against actually knows the entire update history. So although it's static, it can actually a priori choose the best.
That's right. That's exactly right. So we don't get to see the future, but we can adjust our tree. But we are constant competitive with any data structure that can actually see the future. And and so there's an adversary that's determining the future, and we get to, and we're competitive with that.
So is it true for any memory size M, or is there a like the relation between M and?
My guess, that's a great question. The question is, how does this depend on M? So my guess is that this holds when M is at least some polynomially smaller than n, but I actually don't even remember. Do you remember?
I don't remember.
But it's a great question.
So is the Jello tree eventually kind of rebuilding, like using multi-arm bandits to switch between
Yes.
like a slot, as
Right, so somehow the Jello tree is trying to decide, as things go on and there are updates and searches and so forth, it's trying to decide for every node, when it's time to rebuild a node, what the fan out should be next time around and what the pivots should be.
And rebuilding means switching to a different static buffer propagated tree, or is it just?
No, local. Like you locally rebuild a node.
It's not static, it's dynamic.
Right, we're dynamic.
Yeah, I guess what I'm asking is, are you ultimately finding the best static buffer propagated tree, or that not necessarily?
Not necessarily, because we could be much better than the best static.
Oh, I see.
Right, so because the workloads could change over time. So we're not finding the best static thing. We're just going along our own merry way.
Each workload is nothing but insertions followed by nothing but queries. The static needs to compromise, and we just need to learn quickly that it's updates, and then transition quickly once you switch to queries.
All right, so this is the first result, static optimality. And the second result, one of the things that always, I think, surprised me was just how different it is. Like the static optimal which often is much easier, and then there's dynamic optimality, which is usually beyond our reach. But there's actually a continuum between static and dynamic optimality. Because just imagine you've got a workload, your adversarial workload, and the adversarial workload changes, but it doesn't change that fast. Like maybe now you're doing a bunch of insertions here, and then you gradually slowly change where you're doing the insertion. So it's not drastically changing too fast. And it feels like we should be able to converge toward a workload that sort of doesn't deviate from itself too much too fast. And so this is the thing that we can formalize here with this notion of speed limitation. So we say that a buffer propagated tree is k speed limit if it spends at most a 1 over k fraction of its cost on modifying the structure of the tree. So our data structure does a bunch of stuff. It does queries and updates, and those all have cost IOs. And the buffer propagated tree is k speed limited if it also can modify the structure of the tree, like when changing the fan out and merging and splitting and so forth, but it doesn't spend too much of its time on this. And so the theorem said informally is that the Jello tree is also 1 over epsilon competitive against a b to the epsilon speed limited buffer propagated tree. So this is this intermediate notion between static and fully dynamic. And we can think about it in 2 different ways. I'm now basically, I think it's this slide, one or maybe only one other slide. I'm trying to get excited about what are the open questions here. Speed limitation, we can think about it in 2 ways. One way we can think about it is a form of resource augmentation, where we're performing some kind of competitive analysis against an adversarial, some optimal adversary, but it costs the adversary k times as much to modify the tree as it does for us. So this is one way to think about this intermediate notion, which is we have to modify the tree, the adversary does. The adversary gets to see the future, we don't, but it's cheaper for us to modify the tree than the adversary. The other way to think about it is a restriction on inputs, where suppose we want to consider inputs where the properties of the inputs change slowly over time. So where we're insert heavy, where we're query heavy, or update heavy and query heavy, that can change, but it's not going to change too fast over time. But these are exactly the inputs where a speed limited tree is actually optimal. So these are 2 ways to think about speed limitation. And regardless of how we think about it, this is the place where the Jello tree shakes. OK, so let's conclude with some open questions. First of all, is there a data structure that is dynamically optimal against all buffer propagated trees? Or is there even a data structure that we conjecture is optimal? Because we know that the Jello tree is not. So is there actually something that is? Along with these lines, the Jello tree is not a clean, simple data structure and a clean, simple analysis. It's complicated. And it's sort of disappointing that it's complicated. And I don't think ultimately something like this should need to be. So one of the questions is sort of to revisit the tree, figure out what's the clean and right way to do it. And is there actually a data structure that's dynamically optimal against some sort of buffer propagated tree? Then the other question is going back to the beginning of the talk. So we talked about dynamic optimality in internal memory. But what happens if we now throw speed limitations back into the picture? Like, what can we say about splay trees against speed limited adversaries? And we're excited about this, and it's completely open. So I'll stop here.
More questions to Michael?
Yeah.
So you said before that split merge trees are like not the right thing to use sometimes, and so I was wondering if we have do we actually
Those are good questions. So first of all, the nice thing about rotations is when you rotate a node up the tree, you're not just moving that one node up the tree, but you're kind of pulling a whole entire subtree up. So that's the nice thing about rotations is you're lifting an entire tree up a little bit. Whereas when you do splitting and merging, you're just sort of moving one pivot up in the tree. And that's just a weaker, it's just a weaker kind of operation. So we know it's not clear that we have the exact right. It could be that there's a modification of buffer propagated trees that leads to better results that we don't know about. But it is the case that buffers and flushing buffers is the right way to think about updates and insertions and deletions in external memory because it's so fast.
It's also on the optimal. It's on the optimal trade-off curve in the external memory comparison model, and it's on the optimal trade-off curve for the external memory model where you can split up bits, but not for the entire parameter range. So it has all these optimality things going for it that if you don't have buffering, you don't have you're just not nowhere near the optimal trade-off curve.
Could you flash up? So I would like to see again at some point you had the thing where you introduced what you meant by dynamic optimality and you wanted to show what were you allowing to play with, right? So what were the...
Just the very first definition.
I don't know if it's a definition. It was within this, when you were trying to find a dynamically optimal external memory tree.
Yeah.
What is the class of algorithms that you're...
Got it. Yeah. So
you wrote something about that.
Right. And
Yeah, you have a slide on this much later.
Yeah.
I think the simplest way to think about it is split merge trees with buffers.
Right. So split merge trees with buffers, where all of these nodes. So in order to prove bounds, we also have this restriction that the buffers are evenly split among the nodes. So the class of data structures that we were looking like is like this, except different nodes can have different fan-outs, which also means that different nodes will have different depths.
But do you demand that the buffers be the...
I think in our paper we do. It's not clear that it has to be like within a node all the buffers all the buffers have the same size within a node.
There's another thing about this, which is really the flushing scheme is you have one buffer, and when the one buffer fills up, you greedily flush to the child that has the most messages going to it.
Yeah.
It's asymptotically in the worst case the same.
So what I'm trying to... So there is the class of algorithms that you were playing against.
That's right.
So in the class of algorithms you're playing against, you're requiring the buffer sizes to be the same.
That's right.
No.
Oh, no, we're not?
We're requiring them to have a buffer, and when they fill up, they can choose who to flush.
So one could imagine, for example, I've got space B.
Yep.
And I could imagine an algorithm which dynamically decides how to partition the buffers. If it's getting lots of updates that wanted to go
Oh, right,
to the
and
left,
and that's what
then it should,
and interesting. I don't even remember. So that's right. So that's
It
yeah.
is, you have one buffer for the whole thing.
right.
And at any time, actually, you don't even need to wait till it fills up. At any time, you can take messages going to a child and send them there.
Okay. Okay.
And that subsumes
Right.
uneven
Okay,
buffer size.
That's
And
right.
Are you allowed to pass things up the tree as well?
Not in the thing that Martin just said. There are reasons, like there are other models where maybe you'd want to pass things up the tree, but
Well,
no, we
there's
don't.
I'm just thinking of if you've got something that you're accessing a lot.
That's right. Then you'd want to put it
you
up
do
the
wanna
tree.
pass it.
Yeah. So we don't consider that.
Not in this model.
Not in this model.
That sometimes, one version of that is called popcorning, where if you're querying something, you add it in as a message into the root buffer and let it come down again.
That's right.
Popcorns up.
But what you're also hitting at is, which I hadn't realized before this, is in order to think about dynamic optimality, you really have to think very hard about what the class of data structure is that you want to compare against. And sometimes you might be very disappointed that in order to think very hard about what the class of data structure is, you come up with the right class where you can prove something, and then you realize, oh, it's so disappointing that this other data structure isn't quite in that class. That's right.
Questions? I guess one last thing is, so in internal memory, we have, the nice thing about dynamic optimality is we have lower bounds, right? Concrete lower bounds, like alternation bounds. We have complexity measures of the sequence that we can compare against, right? And get, competitive ratios.
That's right.
Are there similar analogs in external memory?
I don't know of any, but I'm sure that people like. I don't right. There are, but I don't know what they are,
Yeah, for
and it's
example,
certainly
there's-
far less. Like there's all of these different measures in internal memory and these different bounds and these different properties, and I don't know how many of them automatically apply to external memory.
I mean,
How many of them
this
don't?
is finally the right model to even study dynamic optimality and external memory, and this paper was last year.
I see.
So,
Okay, but for example, even just trying to, what's the analog of this Wilbur's alternation bound, right? If your sequence alternates a lot, is that a lower bound on any in this model?
I have no idea. I have no idea. Like this. I mean, the reason why we decided to present this is kind of a playground where there's so much that's open.
All right.